Okay, good morning, everyone. In the last lecture, we were talking about the idea of gravitational mass and gravitational field, and today we'll continue along those lines and look at the gravitational field that is created by various sized objects. Okay, so just to refresh your memory, when we were talking about gravitational field, we were talking about a source particle or source mass that is creating this field around it, and we know that this gravitational field is an attractive field. Okay, so any other object which we are calling as a test mass or a test particle, whenever it comes in the vicinity of this field, it will get attracted to the source particle. Okay, so that's how the idea of gravitational field we are trying to conceive. Okay, so again, for example, if there is earth, it's the source particle, it is creating a gravitational field, and any object, an asteroid or a satellite that comes uh, within an effective distance where this field is strong will get attracted towards the source particle, and we can visualize that this field is pointing towards the center of the earth. Okay, so with these red arrows is how we are depicting this field as to where it is pointing. Okay, so uh, the formula that we have to use is this value for g as f of g, which is force of gravity divided by the mass of the test particle, whatever we will put at certain location p. Okay, so our objective will be to calculate the gravitational field at a point that will be created by some other source particle. Okay, and we will imagine that field and quantify it as the amount of field that is existing at that particular point for any unit mass. Okay, so that is how we are defining the strength of the gravitational field. Okay, so it is the force experienced by a unit mass placed at a certain point where we want to find what is the field at that point. Okay, so we'll be using this minus mg by r square formation. Okay, now again to remind you, the m here is the mass of the source particle, okay, which is creating the field. G is the universal constant. Okay, and r is the distance from where we are calculating the field. Okay, so again, we use a negative sign to show that the field is pointing towards the source particle. Okay, not away from the particle. Okay, so later on we'll also look at gravitational potential, but for now, just focus on the field, and let's look at what is the field for different cases. All right. Let's take the first case, and in this case we have 2-point particles. Okay, and these 2-point particles have a mass of m each. Okay, so what we want to do is now we want to find what will be the gravitational field that will be created by these two particles at a certain point here, okay, in space. All right, so for simplicity, what we will do is we will define our axis in such a way that we are keeping this point P on the x-axis, and then both of these source particles we are keeping on the y-axis. Okay, so we have to define certain parameters here. All right, so we can do that. So both have mass m. Okay, and we can define this point P to lie on the x-axis, and then this point P can move along this x-axis, so we can find gravitational field at all the points on the x-axis. Okay, and all we have to do is vary x. All right, and let's say that r is the distance from this point particle to this value P. Yeah, does anybody have any question? Okay, so this is where we'll start. So we have defined our problem. We have defined our angle as well, that theta is the angle. All right. So let's calculate for the first case. How will it look like? So if you look at these particles here, what are these particles doing? These are source particles. They are creating certain gravitational field at this point P. Okay, and we know gravitational field is an attractive field, right? So if you decompose the vector that we have, this G, which is given by Gm by r square, this is the notation, this is the formula we have to use. Okay, so one of the fields that will be created by this particle here, M, will be pointing in this direction G2. Okay, so that is the field that is pointing along this direction. All right, and then we can decompose it into two vectors, one in the x direction, one in the y direction. All right, similarly, this mass here is going to create a gravitational field at this point. Okay, and the gravitational field is going to be an attractive field, so it is going to point in this direction towards M. Okay, and that is given by this G1 point right here. And again, we can decompose in the y and the x axis. Now, because both of these have the same mass, right, the value for the G that is created by this mass is the same. Okay, G n by r square. So by that convention, your value for G1y and G2y, they are exactly the same, except that they are pointing in the opposite direction. Okay, so these y components will cancel each other out. Okay, so all you are left with is, because of the symmetry of the problem, you are left with both the components of the value of field pointing in the x direction. Okay, so you have one component pointing in the x direction because of the mass here, and one component pointing in the x direction because of the mass here. Okay, and so you can add those components up. Okay? And just by geometry, you know that the component will be G1 times the magnetic some of the gravitational field that is created by this point particles is 2g1 cos theta. Okay, so you're just adding both the components in the x direction, and we have to write a negative sign because we know that it's pointing in the negative x direction because it's the attractive force. Okay, so here what you can do now is you can substitute the value for G. We know G is Gm by r square. Okay, and note r is this uh, hypotenuse right here. Okay, because we are talking about field created by this mass. Okay, so the distance r is from this point particle to this point where the test mass is going to be. Okay, so r, we can write it in terms of x and a. Okay, it's simply using Pythagoras theorem, r square is a square plus x square. Okay, and you can substitute that in here, so you will get minus 2, instead of g we can get g m by x square plus a square, and times we have the angle cos of theta. Okay, however, cos of theta, you know, is adjacent side by hypotenuse, so it is x by r, and that is simply given by x by square root of x square plus a square. Okay, so we can again plug that value in here, and what you will get is G will be minus 2gm. Instead of cos theta, now you can write x, and the denominator factor will become x square plus a square raised to 3 by 2. Okay, so again, so this is the result that we get for a magnetic this is the result we are getting for a gravitational field that is created by 2 point particles of the same mass, and just by symmetry we are asking what is the value of the field that will be created along this x-axis relative to this position of these two masses. Okay, and so you get a factor like this. All right, and this looks confusing in the beginning. Okay, so we are writing in terms of x, and we are writing in terms of a, the separation between these masses. Okay, and you can understand this further, that suppose x was 0. Okay, if x was 0, then this point P would be lying right here in the center. Okay, and then what would happen? There would be gravitational field that this mass would exert on this point particle, so there will be field pointing in this direction. Similarly, there will be a field pointing in the opposite direction here because of this mass here, and since both of these have the same mass, then both of these field will cancel, and then this point P, whatever we keep at this point P, will just be stationary, right? So an object that is kept at point 0 here, okay, which is the origin, it will just be stationary and it won't move. Okay, because the this gravitational field basically cancels each other out. Okay, so that makes sense, right? If x is equal to 0, this whole expression g becomes 0. And similarly, if x is much far away from your separation between the masses, okay, what would that mean? That would mean that this point P, whatever we keep at a very far away distance, it just feels like there is uh, some mass here that is applying an attractive force, and that total mass is 2 times the value of this m. Okay, and look at what value you get. If I substitute x is much greater than a, then I can ignore this term here, the second term. Okay, so I get x square raised to 3 half, and my 2 and my 1 over half can cancel, so I get x cube, and I have an x in the numerator and x cube in the denominator, so I get minus 2gm by x square. Okay, so it's twice the value of what a simple point mass would exert, you see. So uh, a mass that is very far away from these two masses, it will feel like the field, the attractive field that this test mass is experiencing would just be the sum of the two masses times the value of g divided by r square. So logically, let's now do for a uniform rod. Okay, there is a rod. It has some length L, and it has some mass M. Okay, and again we will ask what is the gravitational field that this rod will create at a certain position, point P or whatever. Okay, and we can again choose our axis so that this rod is lying along this x-axis, and then we can ask what is the value of that field at a certain point P along this x-axis. Okay. So now somebody wants to take a shot at how we will do this problem.
तो इसमें स्मॉल एलिमेंट ले लेंगे dx x डिस्टेंस में.
Excellent, excellent. That is the strategy. Very good. Okay. So same idea here. Okay. Pehle, you have to first define where your origin is. So let's put the origin at the center of the rod. Okay. Let's consider a small mass element dm. Okay. And that small mass element dm will have certain length dx. Okay. So now you have to be careful. Conceptually, what is happening now? This small mass element is creating some gravitational field at this point. Similarly, if I double this mass element and take twice the length, then even that element will create an additional gravitational field at this point P. Okay, so each of these mass elements is creating some field at the point P. Okay, so we can just use some conventions. We can just define x as the variable that is changing from the origin. So x is this value all the way to dx. Okay, and just like before, what now we have to do is we have to integrate over the mass. Okay, so instead of gm by r square, now we have g dm by r square, and this dm is this small mass. Okay, अब इसको integrate करेंगे. When we integrate this, we will get the entire mass of the object, and we will get the entire gravitational field that is created at point P. Okay, and just by convention we were discussing this dg, it will be pointing towards this source mass element that is creating the gravitational field. Okay, and when we integrate this, we will get the entire value of g. Okay, and we have to use the same idea. The concept was that when you use a uniform rod, if you consider a small mass element, then you can use the term of linear mass density. So you can use lambda, and lambda will be the total mass divided by the total length, or it will be certain dm divided by certain dx. Okay, so the idea is the same. Okay, and here instead of r, what you can write is, let x0 be the distance all the way from origin to the point P. Okay, so you see now we are getting rid of this element r, because r doesn't have any significant meaning. What is meaningful for us is this value of x and x0, because that is defined from the origin. Okay, so what we have done is, instead of writing g dm by r square, mind you, r square, r is the distance between the mass element and the field that is getting created. Okay, because that will be the field intensity created at a distance r from this mass element here. Okay, so instead of r, we can get rid of r, just write x0 minus x, and that's what we are doing. Okay, so minus g dm by x0 minus x the whole square. Okay, so that is our value of dg. Okay, that is the intensity coming from this. So let's integrate this. If we integrate this, all right, so again we can take the limits. Our limits will be minus L by 2 to L by 2. Okay, and instead of dm, we can just write m by L times dx. Okay, so that is our expression here, minus g m by L times dx, and then we have x0 minus x the whole square. Okay, in the denominator. Okay, so now everything is in terms of x. All right, so gm by L is constant, it can come out of the integral. And now we have dx by x0 minus x square. Okay, and you can just again do the integral of this. It's a straightforward function. Okay, and here you just have to do x raised to n plus 1 divided by n plus 1. So you get x0 minus x raised to minus 1 divided by minus 1, and then when you take the differentiation of the function inside, you get a minus 1 again. Okay, so this minus 1 and minus 1, they will cancel. Okay, so you get x0 minus x raised to minus 1, and then you have to plug in the limits here. Okay, and that's what we are doing. So again, note, see, x0 is constant. X0 is a constant value. It is the distance from the origin to any point P where we are considering. What is changing? X is the variable that is changing. Okay, so you have to go back here, and here what we'll do is we will plug in the value of L by 2 where we have x. Okay, so the first expression will become 1 divided by x0 minus L by 2, minus of the second expression will become 1 divided by x0 minus of minus L by 2, so you'll get plus L by 2. Okay. And here you can just take the LCM. If you take the LCM, you get x0 plus L by 2. There is a factor here on the first term, and in the second term you will get x0 minus L by 2. So you have minus of x0 minus of L by 2, so it will become plus L by 2. You see, so x0 or x0 will cancel again, and you are left with L by 2 plus L by 2. So that is L, and you have the denominator x0 square minus L square by 4. That is just the LCM here, a plus b, a minus b. Okay, and the factor is gm by L. Okay, so L will cancel again, and now you have simplified it as minus gm by x0 square minus L square by 4. Okay, and this is your expression for the magnetic field in the x direction created by a uniform rod. Okay, and it depends on the length of the rod. See? Right? And again, this expression should make sense. What if your point that you're considering is very, very far away from this rod? If it is very, very far away from this rod, then again this rod will look like a point particle. Okay, so we can substitute that. If x0 is much, much greater than L by 2, right? So then here, basically, you are ignoring the second term. Okay, and then you again get minus gm by x square. So again you get the right expression, that the rod behaves like a point mass if you are considering the effect at a very, very far away distance. So now you can imagine the next one is going to be a uniform disk. Okay, so now we want to find the gravitational field from a disk at any point P. Before you calculate for the disk, what you have to calculate is for the ring. Okay, now this ring, you can see it in green. Okay, so as I increase the width of this ring, I will eventually get the disk. Okay, so that was the idea. First take a small mass element. So instead of directly calculating for the disk, first you have to do is calculate for the ring. Okay, so let's see what is the value for the gravitational field that is created by a ring. Okay, so idea is the same. Again, we will consider a small mass element dm. This small mass element is creating some gravitational field at certain point P. Okay, we can just keep it along the center position here just for symmetry. Okay, and we can define this A as the radius of this ring that we want to find. Okay, now capital R is the radius of the disk, mind you. Okay, so that is the radius of the entire disk. Okay, and capital M is the mass of the disk. Okay, so first let's find for the ring. Okay, so for this ring, if you look at the symmetry of this problem, okay, there will be some attractive field that is will be created by this mass element that will be pointing again in this direction right here, right? That will be pointing in this direction right here. Oops. That's this direction right here. Okay. Similarly, there is a mass element on the opposite side of the ring that again will have some field that will be pointing in this direction. And again, we can decompose the components and you can see that the y components will cancel. Okay. So whatever y components are for these two mass elements, they will cancel. So you are left with only the x component. Okay. And this x component, again, if we integrate the small mass element throughout this entire ring, then we will get the total gravitational field that is created by the ring. Okay, and that's what we're doing. Okay, so we have this value of minus g, and then you have the mass. So this mass will be dm, and then instead of g you have the cosine value, because now you have to look at only the factor along this angle here. Only this value is what you have to consider. So that is a cos theta term. Okay, and then you have divided by s square. Remember, s is the distance of separation between the mass and the point where we are considering. Okay? So don't get confused. Don't write x. That would be completely wrong. Okay. So if this is the mass element, then the separation of distance is s. Okay. And s again we can write in terms of your x and a. Okay. So s will just be square root of x square plus a square. So that is what you can do. Okay. So here we will have minus g dm, and g is constant, so it can come out. Okay. Instead of s, we can write x square plus a square. Okay, and it's square, so we will get x square plus a square term here. Okay, and dm stays as dm. Instead of cos theta, we can write cos theta is x divided by s, which is the adjacent side divided by the hypotenuse. Okay, and so that you will get x divided by x square plus a square raised to half. Okay, so your denominator term will become to the power 3 halves. Okay, and in the numerator you have g and x. And note, see, all these things are constant. X is constant for this entire ring element. X doesn't change. X is from the center of the ring to this point P. It doesn't change. Okay, a is the radius of the ring. It doesn't change. Okay, so those are constants, so they can come out of the integral. Okay, and when you integrate the entire mass, then you just get m, which is the mass, small mass, and this small mass is of this ring. Okay, so don't get confused. We are trying to find first for the ring. So you get an expression that for the ring, your value is minus g small m x divided by x square plus a square is to 3 half. Okay, and that is the expression for the ring. Now that we have the expression for the ring, we can integrate this and increase the size of this ring to get the value for the disk. Okay, so that is what we'll be doing. So you have the disk, it will go all the way from 0 to r. You will go from all the way 0 to r, and you will integrate it and increase the width of this ring. Okay, and now this mass can change. So let's take now this mass to be a small mass dm as compared to the mass of the disk. Okay, so you get dm as a small mass, and then you have x by x square plus a square is to 3 half. Okay, so that is your starting expression now for the disk. And again we will use the same idea. We have the surface density now, because we are considering the disk, which we know is mass by area. Okay, and for this small mass element of the ring, the entire ring, now you will have the area will be 2 pi the perimeter, right? So 2 pi a times the dA, the width. And so now we are changing dA. Okay, and as we change dA all the way from 0 to r, we will get the entire disk. Okay, and that's what we are doing. So again, g is constant, it can come out. Okay, limits are 0 to r, x stays as it is, dm is given by sigma times this capital dA. Okay, and in the denominator you have x square plus a square is to 3 half. Okay, and again sigma we know is constant, so it can come out as well. Okay, and x again is constant, it can come out, and instead of dA now you can write 2 pi a the little dA. Okay, so that is the expression here. divided by x square plus a square. Okay, so again you can simplify it further. There is a pi here, it will cancel with the pi. Okay, so you get minus 2gm by r square, which is this expression right here, times x, right? And now you are integrating 0 to r a dA by this factor. Okay, so again you have to do this by substitution. Okay, so we will consider x square plus a square to be u. Okay, and if you do that, then we can write a dA as du divided by 2. Okay, just like we did before. Okay, but we have to change the limits of the integration. As a is 0, you get u is just x square. Okay, so that is what you get. And as a is r, u will become x square plus capital R square. So those are your limits of integration. Okay, and a dA becomes du by 2, and x square plus a square becomes u, and so you get u raised to 3 half. Okay, so that is your expression right. So now we can easily integrate this. You have minus 2gm x by r square stays the same, 1 half comes outside, and this expression becomes u to the power minus 3 half. And then when we integrate this, I have to add plus 1 here, and then I have to do minus 3 halves plus 1, right? So that is my integration of u to the power 3 half. Okay, so this is the expression I will get, u to the power minus half divided by minus half. Okay, and again half and half will cancel, minus and minus sign will cancel. Okay, so you are left with 2gmx by r square, and then you have to substitute the limits here. Okay, so this is a rather lengthy one. Step by step you can follow it. So all you have to do is you have to plug in this value now to get 2gm by r square x times 1 by x square by r square raised to half. Remember, there is a half factor here. Okay, so there is a square root factor, and you have minus 1 over square root of x square. Okay, so you can just multiply x inside, and this is the expression that you will get. Okay, which is a rather lengthy one, and it is non-intuitive. I mean, we cannot tell by intuition that the g for a disk will be this factor. Okay, which will be minus 2gm by r square, and I have taken a minus sign so that our convention is followed, that it is attractive force. Okay, and just to be correct, we can just write this as g, and we can write this as I, so that we know which direction it is pointing. Okay, and I have changed the values here, so I have taken a minus sign outside, so I get 1 minus x by x square plus r square raised to half. Okay, and this expression might look very weird in the beginning, but you see, if I just use some approximation and say what happens again when x is very, very far away from r. That means this point is very, very far away from this disk. What happens in that case? So in that case, here this expression, you can simplify it further. Okay? So if I take x outside, I get 1 plus r square divided by x square raised to half. Okay? So square root term, and there is x square, so I get an x term outside, and x will cancel. Okay, so I am left with 1 plus r square by x square raised to minus half. And remember, we are again using Taylor series expansion. Very useful. Okay, Taylor series expansion, where we are saying that 1 plus x raised to n is just 1 plus nx, and we are ignoring the higher order terms. Okay, so again 1 plus n is minus half, so you get 1 minus half times r square by x square. So that is what expression you are getting with 1 minus r square by 2x square. Okay, so this function gets simplified into this expression. Okay, so that is the second part here. So if I use this now inside, I get 1 minus 1, minus of minus, this will become plus r square by 2x square. Okay, and you see 1 and 1 will cancel, and r square will cancel right here. Okay, and 2 and 2 will cancel, and so again I get minus gm by x square. And what is this value? This is the value of a field that is created by a mass m at a distance x, considering that this mass m is a point particle. Okay, so again, if you take a disk and you go very, very far away, and you ask at this far away distance, what is the gravitational field created by the disk? This point P, it feels like to it that this entire mass is just concentrated at a single point in space. Okay, and the whole problem again simplifies to the same result. Okay,